Discrete probability distributions. Basically, before today, or before now, we have collected data based on a situation. We have calculated probabilities of a situation. Now what we're going to do with discrete probability distributions is create theoretical models so we can predict and make judgments on a population based off the data we collected. A lot of the ideas are going to be very similar to what we learned before. For example, to find the mean, you are going to sum up all your data points and multiply it by the probability, where probability is basically, we learned from the previous chapters, where probability is the number of successful events divided by the total. So in reality, we are adding up all of our data points and dividing by how many there were, which gives you the average. So this is taking ideas that we already know and just writing them in a different format. An idea that is introduced in this chapter is the expected value. The expected value is given a situation, say, for example, gambling. If you want to find your probability of winning, or if you play the game enough times, would you make a profit or would you not make a profit, you would calculate the expected value, which is basically just the mean. Similar to before, our variance, which is our standard deviation squared. It's calculated the same way, it's just written differently. So you would take your data point, subtract the mean, square that difference, add them all up, and you would get your variance. We are just using the idea of probability, which is, again, successes over your total population. So it's taking the same ideas and just writing them with probability notation. You're going to see both of these formulas for variance. They mean the same exact thing. It's just they took this formula, did a whole bunch of calculated algebra, which I'm not going to go into now, and they simplified it to look like this. This formula is a little bit easier to understand. It's more related to variance, and this one is easier to calculate by hand. So they both have benefits, and they both say the same thing. And standard deviation is the same formula for variance, except we take the square root of both sides. So it's not going to be variance squared anymore, because we took the square root of both sides. Probability properties still hold. So if you were to add up all your probabilities of a distribution, it should add up to 1. Your probability will always be greater than 0 or equal to, or less than or equal to 1. So probability will always bounce between 0 and 1, and if you add them up, add up the total events, you should get 1. If you get 0.99 or 1.001, that's still fine. That's probably just due to rounding error. Another idea that is from previous topics in statistics is significant values. These come into play when we are trying to make decisions or judgments on a population based off data we collected. So we call those judgments or ideas hypothesis or hypothesis testing. So we collected our data, we organized it, we calculated probabilities, and now we're going to make a judgment on the population. Then we're going to test our hypothesis. This is something we're going to be doing in later topics of statistics. We're going to test our hypothesis and see if it fits to our data or not. If we test our hypothesis and it lands inside the 2 standard deviations of our mean, we would say it's not significant, meaning that based on the data we collected and the hypothesis we came up with, when we test that data, it is not significant enough to reject this hypothesis. So whatever that hypothesis is, based on the data we collected, we cannot reject the hypothesis. We're not saying it's true, we're just saying we don't have enough data to say it's false. Whereas if we have our hypothesis, we collected the data, we analyzed it, and we see that our collection lands within 2 standard deviations away from the mean, so in this case it's to the right, or if it's 2 standard deviations to the left of the mean, we would say it's significantly low. So if we get something that's significantly low, we will be able to reject our hypothesis. Because based on our hypothesis, we should be closer to the mean, but since we are way outside here, it's significantly low, which means we can reject our hypothesis. Similar idea, if we are 2 standard deviations above the mean, we would say it's significantly high. And since it's significantly high, or way too far away from our accepted mean, we would reject our hypothesis. Again, these are ideas we're going to conquer with later topics of statistics, but it's helpful to know that when they're talking about significant values, if it is within 2 standard deviations of the mean, or within this window, it is not very significant. If it is outside those barriers, it is significant. Another idea in statistics is binomial probability. This is strictly when we're calculating a probability of a situation where there's only 2 outcomes. Those outcomes are usually success or failure. Did I get heads or did I get tails? Did I roll a 6 on a 6-sided die or did I not roll a 6? Okay. To find the probability, we use this formula, which I will explain in a second. For example, we have our P is the probability of success, which means we have probability of failure. To find the probability of failure, you're just going to do 1 minus P. N is the number of trials, X is the number of successes. So for example, we wanted to roll a 6-sided die 3 times. I want to find the probability of rolling 2 6s. So the probability of rolling 1 6 would be 1 out of 6. The probability of rolling a second 6 would be 1 out of 6. And the probability of rolling not a 6 on that third roll would be 5 out of 6. So this would be one scenario where we would roll 2 6s from a 3-sided die from a 6-sided die on 3 rolls. The only thing is, these can happen in any order. We can have, so for example, we can roll 6, we can roll not a 6, then we can roll 6, or we can roll not a 6, then 2 6s, and so on and so forth. So what we got to do is we have to account for all those different scenarios, all those different orders, which brings us to our idea from previous chapters, combinations. So we are going to roll it 3 times. We're going to see how many times we can roll 2 6s, or how many different orders. So this takes care of the different number of combinations of these situations. And we are going to multiply for the probability of successes, which in this case is 1 over 6 to the second power, because there's 2 of them, times probability of failure, which is 5 over 6, and there's only 1 of them. This is basically this formula. So if you look at the similarities, you can see that we have 3 trials, so n trials, 2 successes for the x's. We have a probability of success, we have a probability of failure. Okay, so that formula is only used for binomial probabilities where we have a success or we have a failure. And last idea, we have the Poisson probability. This is a probability where an event is occurring over a specified interval, where that interval being area of a field, length of time, what have you. Basically, we need to take into the idea of continuous. So the probability for a Poisson probability is found using this formula, where this is our mu, or our mean. X is the event. And E, I'm not sure if you have seen this variable before, but E basically takes care of continuous events. So to find E, we would use this formula. This is a calculus idea, but since we're in statistics, you can just know that the value of E is approximately 2.71828. Okay? Okay, so again, Poisson probability is an event that's occurring over a specified interval. We would use this formula where we would know our mean, we would know the number of events, and we know what E is. It's approximately 2.71. Then we have the idea of binomial probability, which is where we have only two situations where it's success or failure, and we would use this formula. Significant values, if it is within 2 standard deviations, it's not significant enough to reject a hypothesis, and if it is outside those standard deviations, it is significant enough and we can reject. So if it's inside, we fail to reject. If it's outside, we can reject. And that sums up discrete probability. Stay tuned for more videos.